major and a math minor. I'm a sophomore here at Northeastern, graduating in 2015. That's me sitting in my office this summer. And here is where I was. I was at the University of Alaska Fairbanks working at the Geophysical Institute for 3 months. This is actually a picture of right outside my office looking into downtown Fairbanks. And I had an REU there working with 3 other students, and those are our professors. So how did I get there? If I had to say my first step towards research, it would be through PRISM. I have been involved in PRISM for as long as I've been at Northeastern. I started in the summer discovery program. In preview, I did the lecture series, I did the spring class, I did the summer discovery program. And in the spring class and the summer discovery program, that's where I first learned MATLAB, which was incredibly important for my REU. And this is also when I started working on my own research projects. And these included things like looking into the greedy algorithm or using the equipment in Professor Sternad's lab to design our own experiment. What we did was we looked at handwriting and how different grips affected it. So I had this experience, and it really was this experience in the lab that cemented my desire to do research, to actually be in there and doing things and discovering things that no one had thought to discover before. So where do I go from there? I didn't really have any idea until I heard Emily speak last year talking about her own experience with REUs. So I decided to apply. I applied to 6 all around the country, and I was accepted into the one in Fairbanks. So I have a lot of advice if REUs or any like summer internships is what you would be interested in. The best thing I think I did was talking to my co-op advisor, because she had a lot of advice and support for me while I was doing this process. And I also didn't limit myself at all by geography. I know there are a lot of opportunities in Boston, but those ones probably also have a lot of competition, so you may want to consider looking further than just the immediate area. And also, I guess that was for personal reasons, because I got to go on a huge adventure. What's more adventurous than going 5,000 miles away from your home? If I had to do this process again, I would start a lot earlier than I did. Although the National Science Foundation funds these programs, they don't have like one universal application. So it took me a lot longer than I would have expected. And each application ranged from, say, a 1-page form that you had to fill out to multiple short answer questions and resumes and getting letters of recommendation. I also would have looked outside my major. I only applied to REUs that were listed as physics REUs, where I could have just as easily gone for a math one or a chemistry one. They're designed to be interdisciplinary. I was working with another physics major, but also a chemistry major, and a girl who was so undecided she didn't even know if she wanted to go into science. So you should definitely explore all your options. I wish I didn't limit myself that way. In terms of classroom work, nothing, well, only PRISM directly helped me, because that's what taught me MATLAB, and I needed that for the programming for my REU, and then I also used the knowledge I had from MATLAB to learn a different language, which was VI. I had to learn a lot of different commands to implement the larger program. And the science and math classes I had taken here helped me in that they built a foundation and I could build up on that, but it was a lot more important that I knew how to get the information I needed. I was lucky enough that there was a library right downstairs that I could go to and brush up on chemistry, atmospheric science, thermodynamics, volcanoes, anything at all that I could have possibly needed to know about. Volcanoes are hilarious. And so here are my main suggestions. Apply even if you don't think you will get anything. I thought there was no way I would be accepted into any of them since I applied to so few, but luckily I got into the Alaska one and that was the last one I applied for too. So always apply to one more than you think you should. You also need to talk to professors early because you do need to be building these relationships. So they feel comfortable and will have time to write you the letters. Also, as a heads up, most REUs require 2 letters of recommendation. You should also double check all the requirements. Some require you take certain classes. For the physics ones I was looking at, most required that you had taken at least up to modern physics. Some only accept juniors, so it's really tricky to find some if you want to get in right after your freshman year, but they're there, so you just have to keep looking. And each application is different, so they can make any sort of requirements they want, which is unfortunate, but and you need to always have a backup plan. I thought that if I hadn't gotten in any of the RUs that I would try to get into research on campus, and maybe if that didn't work, I would try an internship at the Museum of Science. Basically, I wanted to do anything but work at Dunkin' Donuts again that summer. Okay, so here is what I actually did. There has been notable increase in sulfate aerosol concentrations in the Aleutian Islands for the past 10 years. And there are different sources. We're not exactly sure what could be causing this increase. It could be things like just people living there, or there's a type of algae that produces this aerosol. It could be passing ships, or it could be volcanoes. But first, there's a problem in that the computer model we're using made SORGAM, which is Modal Aerosol Dynamic for Europe / Secondary Organic Aerosol Model. It was designed for Europe, and it works fine there and in the lower 48. But in those places, it never gets very cold. Whereas in Alaska, it regularly gets to -50°C in the wintertime. And the model doesn't completely account for temperature variation. There are many parameters in it that are truly based on temperature, but weren't designed that way in the model. So I did literature research to fix that. And this graph on the left was from the original model, and this is from the modified, with the variation that I put in place. And as you can see, for like the right half of each graph, they're identical, which is good because it was in this range where the model was accurate. But as you get to like -50-ish, like -35, there is a lot of variation. And now this is more accurate because it's using the parameters the way they are in real life, and they are, and it's accurate for the entire range as opposed to just the warmer range. And then they will be using the modifications from now on. And we also looked at it with volcanoes and found that volcanic activity is one of the reasons why the aerosol concentration is increasing. So, does anyone have any questions? There's also my email address if you would rather email.
What was it like working in Alaska?
it was pretty awesome because just with the research, just tying it in with the research, like everything I was doing there, I could go out and see in real life. One of the reasons human beings will increase aerosol concentration has a lot to do with pets. And in most places, they don't really need to put that into consideration in the model, but in Alaska they do, because I personally met someone with a sled dog team. there are people who have like 80 dogs in their backyard, and that is really, it affects the aerosol, and that's not something you would find around here. So you can go out and see why things need to be so modified for Alaska, even though it's part of the United States. It was also really, really pretty there. You should go if you ever get the chance. Any other questions?
Can you hear me through this?
Yeah.
Okay. So, hi, I'm Brittany Haffner, and this is my presentation, Undergraduate Research in Action. I thought it was pretty funny. So, throughout me, I'm doing a pretty special program. It's a combined BS-MS in Applied Physics and Electrical Engineering. It's an integrated bachelor's and master's program where I get both a bachelor's in Applied Physics and a master's in Electrical Engineering all in 5 years. I graduate in 2014, and I'm actually currently on my first co-op in the Action Lab with Dr. Stern. Okay, so my journey to the Action Lab had a lot of twists and turns. I had a very incredibly frustrating co-op process. A lot of places didn't really accept very many first-time students looking for co-op in physics because a lot of us didn't have a lot of undergraduate research experience or any experience whatsoever. So I applied to probably 30 or 40 jobs on NU Pool and didn't get any of them. So I was pretty upset. However, I was a TA for Enhancing Honors too, and that's when Dr. Stern came in and spoke a little bit about what she does in the Action Lab, and I realized that it sounded like a really cool experience. So as part of a co-op class, we had to do an assignment where we did an informational interview with a professor or someone who's studying something that we find very interesting. So I called her up for the interview, and out of that, I became a test subject in her lab doing Skittles. And then after I was a test subject, I decided that I would love to work there. So a couple weeks later, I finally got up the courage and asked her if I could have a co-op, sent her my resume, and here I am now. So we already had a little bit of a background about the Action Lab. We do a lot of motor control and motor skill learning, and some of our tasks include like Skittles, ball bouncing, the haptic master with their cup of coffee kind of thing. There's a bimanual task where subjects are asked to move their arms on these manipulandums in different ratios. And then we have a new motion tracking system where we have 12 cameras set up around the lab, and they look at the different markers and look at movement. So that's what we do. However, what I do is a little bit different. both of the projects that I'm on actually don't really have much to do with motor skill learning. The first project I've done is the ball bouncing, but instead of using it in terms of learning, we're looking to see if the heart rate will actually couple with rhythmic frequency generated by the body. And then the second project that I actually kind of just finished up, I was working with an associate professor who was visiting from Arizona State University on her sabbatical, and we were looking at postural control. We were basically trying to find a dynamic model for the human body as it maintains a standing posture. I'm not sure if any of you have heard of like the inverted pendulum. So basically, a lot of models for the human body state that we are an inverted pendulum, and there's at one point and we swing. Obviously, it's not that great of a model. I mean, it gets the job done, but it leaves out a lot of factors and a lot of body angles. So basically, we're wondering, why can an auto rocket stand on a skateboard while Sam falls off? What keeps us standing? What keeps us balanced? So for our ball bouncing setup, I'm sure some of you have seen this before, but we use a Colburn ECG, or some of you may know it as an EKG, and we use 3 limb leads to measure the heart rate. And then we have an actual ping pong paddle connected to an optical encoder so that you can see the virtual racket and a virtual ball on a screen in front of you. And then we ask the subjects to bounce the ball at a rhythmic frequency. And then we can also manipulate the frequency at which they bounce the ball by manipulating the target height. So if we want them to bounce it the ball slower, we increase the target height. If we want them to bounce it faster, we lower the target height. Okay, so what we actually look at, on the top left here, the blue is the ECG graph, so you can see the R waves, which are the taller ones, and then the black is the racket movement. As you can tell, it's sinusoidal, and that's because we ask the subjects to move at a consistent pace. And then the circles are the peaks, or what's signified the event taking place. As you know, the heartbeat isn't just some burst, it's actually a process. So when we have to look at the frequency of the heart rate, or something continuous like that, we need to have something to count, something to trigger. And here on the bottom right, we have the periods. The blue is the interbeat interval, or the time in between each heartbeat, and the green is the period of racket movement. And so we're looking for the correlations between these 2 signals, and is there a relationship between the periods of the heart rate, or the heartbeat, and the periods of the racket position, and is there a relationship? Okay, and my second project is the postural control project. So like I said before, there are 12 cameras around the lab that look down on a small area of the lab, and we have 11 markers for this particular project. On the left side of the body, we are looking only at the sagittal plane, so just looking at the Z component and how you move forward and backward. And then we have 7 muscles monitored by a wireless EMG. That's all the blue flashing lights you see around. And the actual experiment is conducted on force plates, and some of the trials actually we tried to invoke some sort of motion. So we had subjects stand on different sized bars. There was a bar that was so narrow that sometimes subjects just fell off and couldn't stay on for the full 20 seconds of the trial. However, there was one test subject that managed to stay on for a couple minutes. So this is what we will look at. We just now finished collecting all the data, and so we're going to analyze it now. And in the top left, this is the marker location. So here's the foot. We have the heel, the ankle, and the toe, knee, hip, and so on and so forth. This is the upper body. The subjects are asked to stand with their arms crossed in front of them. And we use those marker placements to help find the center of mass. And then we also look at the EMG data, and I specifically showed rectus abdominis, and that's basically your abs. And obviously this person had to be moving a lot because they were engaging their abs in little bursts. And then we look at the components of force, and it's kind of, you can see there's periodic motion, so this means that the subject is swaying. We look at other things too, like center of pressure, center of mass, but these are some key components that we look at. Okay, so looking back, what I'm glad I did is, even though I went through that long, frustrating co-op process, I'm glad I did take the initiative to go out and talk to a professor who sounded like she was doing something very interesting, and it was very interesting. And then I'm also glad I read up on the research before starting my job. If you do get the chance to work in a lab and you do have access to any of their work, I do suggest that you read some of their papers. It may be a little bit hard to get through if you have no idea what's going on, but you need to have some sort of idea of what the research is before going into it. And then I also, after I got there, after a couple of months, I did end up asking for more work around the lab, and that's how I got my second project. And I'm really glad I did it because everything you can do to help you learn and help you grow in this experience is something you should really do. What I would have done differently, I wouldn't have waited till my middle year to get into undergraduate research. So the fact that you're considering doing it, before co-op or in your freshman and sophomore years is really a great thing, especially when it comes to finding a co-op or finding more experiences in undergraduate research. And then I also wish I had networked earlier on. I mean, I did have some good relationships with professors and spoke to them frequently, but I didn't really network. I didn't really ask them about the research they were doing or ask them what kind of research they thought that would be good for me. And that ended up kind of hindering me in the beginning, but now I've learned better. And I also wish I had practiced my programming a little bit before going into work. I had taken a general engineering course and learned MATLAB and C++, but I wish I had gone back. It would have helped me for the first week a little bit. And then looking forward, this was great preparation for the electrical engineering classes I'll have to take. As you had seen before, I do a lot of signal processing in the action lab. And I'm also more confident in my programming abilities as well as basic physics and math skills. I've always loved math. Unlike some of the other speakers, I always loved math. It was one of my favorite subjects. And I'm actually grateful that I get to apply some of math and basic physics skills to what I do. I'm hopeful that I know it's not going to happen the next couple months, but hopefully I can stay involved with the Action Lab and be a part of 2 published papers by the time I'm done with my experience here. I've also obtained a skill set that I know I wouldn't have been able to had I not been in undergraduate research. You learn to think outside the box. You really learn to problem solve. I mean, yes, you have to do that in class, and yes, class kind of prepares you for these kinds of things. But now it's, you feel like you're in the real world. Your problem solving actually yields something. And undergraduate research does open the doors to a plethora of opportunities. I mean, we've already had speakers say that it helped them in industry, it helped them in other undergraduate research, and it's really a great opportunity and something you should really consider. So, any questions?
Could you say us more about how you wish you networked more earlier?
Okay, so I wasn't very aware of how important undergraduate research was. So although I did come to my professors a lot freshman and sophomore year to ask for help and to learn more about the subject, I didn't ever ask them about their research. Or I didn't ask them to point me in a direction that I thought would be good for me, or ask for names of someone who's doing research that I might be interested in. Any other questions?
What do you think is the coolest part about working in the Action Lab?
A lot of fun toys. I will. I enjoy also being a test subject, and I'm sure you must have done this in national opportunity. You work on your own project, then you also get to be a test subject in someone else's project. And it's a lot of fun. I mean, especially all virtual stuff.
You had several, I think almost everybody has commented about the importance of MATLAB.
Mm-hmm.
And so I'd like to ask generally what we could do about that. I mean, what are the really positive parts of that? What have we done about that that's not so positive?
Mm-hmm.
And not just you, but everybody. I'd like to hear.
Well,
I want to learn from you.
Okay. Well, as a physics major, we have to take, I don't know if you had to do it in your year, but we have to take a general engineering course that teaches, it's general engineering, problem solving, and computation. And engineers and physicists have to take that. But I think anyone who wants to go into some sort of field of science, I think there needs to be a class for everyone to take. Because it is, you have to collect data if you're in a science field, and you have to then analyze that data, and MATLAB is a great tool for that. So I really think there just needs to be more classroom opportunities for students to learn MATLAB.
So it sounds like there should be a separate course which not just teaches programming, but teaches somehow using the programming to understand something that's not just the programming.
Oh yeah, and well, the way that the general engineering class does it is you don't just learn commands. They give you a problem to solve, and then you have to implement what you've learned in the classroom into a program. And sometimes you'd be at the lab for 5 hours at a time for 3 days straight trying to finish your weekly assignment. So they made sure that you really learned it. So I don't think the class itself needs to be changed. It just needs to, I think, be more open. Or there needs to be a class for everyone to take where they learn programming.
Anybody else?
I'm glad that we got some exposure to MATLAB and PRISM.
Yeah.
That was really useful.
That was the first time I was exposed to it. So if I had just followed the normal bio undergrad, I would never have seen MATLAB with the exception of PRISM. I could have done tons of research and desperately needed it.
Yeah.
Never would have happened to it.
Mm-hmm.
And to add on to what you said, for when we were doing it in PRISM, we had to do it to solve problems. And then I got to Alaska and I had to not only program for my own project, but then do all the programming for the other boy I worked with, because he was doing something on window profiles and didn't know any MATLAB. So I had to program for his without really understanding what he was doing. So I had to learn more and figure out how to